So today, first thing I want to talk about is about paper chromatography. So I will show you a presentation there. Let me take a look. Yeah, right here, okay. Okay, thin layer chromatography. And so here I just want to talk about principles and some applications. I believe you all did this experiment before, but probably in different form. For example, if we just use a paper or sometimes with some thin glass pieces. So if we dot it with different compounds or sometimes mixture. So let me use a laser pointer. So for example, we have 3 different dyes. We can dot them here at the baseline and put another mixture, mix it with 2 compounds. Then we dip this TLC into a solution. Solution can be different things. Usually they are there's an organic solvent. So dip into there, let it run for a few minutes, sometimes 5 minutes, sometimes 10 minutes, based on what kind of thing. So, and you can see those dots can move upwards. And when you stop it, you can see that there's a front, solvent front at the top right here. And you can see the dot moves. Sometimes there are some colors, sometimes they're just white dot. For most of the cases, you even can't see them. But we can use the UV vis light to show them, to shine on them. Then we can see those shining dots. That's something like a forensic chemistry, something like that. So then we can compare their distance from the baseline. Then we can tell, all right, because dye 1, 2, and 3, they're standard compounds. We know them already. Then we compare to the mixture. Oh, there are 2 compounds in this mixture, and one is dye 1, the other is dye 3, and there's nothing related to dye 2. Then we can identify this mixture containing 2 compounds. Okay, so that's the way we do that. Okay, here I just want to talk about some principles about TLC. So there are 2 phases, basically. One is a stationary phase. The other is a mobile phase. Mobile phase is basically the solvent, organic solvent. The stationary phase is the solid on the paper or on the surface of glasses. There are 2 phases. The solid phase, usually we use a silica gel. Basically, it's like grass or like sand. Okay, it's very polar, and usually is acidic, very acidic. Or sometimes we can use let me think. Somebody join here. Sometimes we use aluminum oxide as a solid phase. It's also polar, but based on how do you make them, it can be neutral, basic, or acidic. The good thing, the advantages of this technology is very sensitive, very fast. It just need very little amounts of the compounds. It's very simple. Okay, you don't need to set up a very complex equipment, and it's inexpensive, usually quite cheap actually. All right. So here, let's just take a look at the atomic level. So usually we have a backing. It could be paper or glass. Let's say glass is the most common one. So then put a film on it. The film here is shown here. This is a silicon dioxide based. So on the surface here, there are a lot of hydroxyl group, OH group. Okay, like in a lot of oxo acid. That's why we say it's acidic, because this is more like a weak acid. Here we have two compounds. I just put two compounds here. pH means a phenyl group, like benzene ring. Okay, so this is a toluene, and this is here is a hydroxyl group with the CH2 and connect to the benzene ring. But doesn't matter. It's a nonpolar. Okay, this is a very nonpolar. That part is nonpolar, but we got a hydroxyl, but we know it's like something like water. So this is very polar. And because there are so many hydroxyl groups on the surface, so they can form a hydrogen bonding with this compound. But for the other compound, which is nonpolar, so the IMF, intermolecular forces, are only dispersion forces between them. Okay. Oh, of course, there's a dipole dispersion, this kind of thing, but apparently there's no hydrogen bonding network formed between them. So when the solvent runs from bottom to top, because there's a hydrogen bonding network between the surface and between the solid here, we call it a stationary state phase, and this compound here. So it's kind of stuck here. It can't move very quickly. While the other one is nonpolar, there isn't a very strong intermolecular forces between them, so it can move fast. So that's why you can see the separation between them in the end. So IMF is the reason why they can be separate or identified. Okay? You get it? So that's the principle. Okay? So the conclusion is that the more polar the compounds are, the slower the compounds move. Get it? That's the conclusion. Okay? Let's move on. Here is a typical, here is the cartoon for a typical condition. For example, so here is a baseline. We said it's just, we call it origin. Okay, then we dot 3 spots here with 3 different compounds. Then let it run in a solution. Okay, in a solvent, sorry, organic solvent. Then the solvent runs at the top here, then we stop, so we can see the 3 dots shown here. And then we can just use a ruler to measure the distance from origin to from, oh, let's say it's 10 centimeter, and here C is 8, then B is 5, A is 2. Then we can do calculation. We call it RF. RF means retention factors. So for A, it's 2 divided by 10 equal to 0.2. Then we have a 0.5 for B, 0.8 for C. So from these values, we can tell, okay, the greater the value is, the molecule, the more polar, more nonpolar, let's say, okay, the more nonpolar or the less polar the compound is, okay. The value can indicate how polar it is, how polar is it. The big value means it's nonpolar, small value means it's very polar, okay. You get it? Okay, so there are a lot of applications, so we cannot talk this here a lot. So if we use a TLC, thin layer chromatography, we can determine how many compounds are there in the mixture, okay, because they can be separate, and identify two or more substances compared to standard substance we have. And sometimes we can use it to purify, okay? And sometimes we can use it to set the condition for a column chromatographic separation. So that's just there. Of course, there are many more applications. Another thing for reactions, we can monitor a reaction, the progress of reaction. That means, for example, we have reactant and product. So if the reactant and the product they have a different polarity, so then we can at a certain time we can get some solution of the reaction and put a dot on the TLC. Then we can see, okay, the amount of the reactant, the amount of product. Okay, so that's a very easy way to do that. It doesn't need a lot of a large amount of the from the reaction. Okay. Okay, so let's just stop here and start to work on the problems. So if you have any question, you can raise your hand and or unmute your unmute your microphone and ask me a question. Okay.
Mr. Fan, when you said the less polar it is, the slower the molecule moves?
Yes.
Okay.
Yeah, the polar, you still remember that? So because there's a strong bond, because of the solid phase, okay, stationary phase is very polar. So if the molecule is very polar, there are very strong interaction between them. We just like you have something hold it back a lot. Get it?
Okay.
So if it's non-polar, there's no such a strong force to hold it back, so it can move fast. Okay. So you always remember that. You can tell the result. Okay. All right. So let's move on to the question now. Okay, let me share the window with you. So the first question we talk about is about the paper chromatography, which is the question 4 in 2017 AP Chemistry exam. Okay, so now I think it's easier for you to solve this problem. Okay, let me just use the laser pointer. Okay, the question here. So a student investigates various dyes using paper chromatography. The student has samples of 3 pure dyes labeled ABC, an unknown sample that contains one of the 3 dyes. The student prepares the chromatography chambers shown above on the left by putting a drop of each dye at the indicated position on the chromatography paper. It says it's a polar material, so as usual. And staining the paper in the non-polar solvent, the solvent usually they are non-polar, okay, but it's here the question it's quite clear. It's just indicates it's very clear, okay. The developed chromatograms are shown above on the right. So here's the question. No. Yeah. Okay. So first question, which dye, A, B, C, is the least polar? Justify your answer in the terms of the interaction between the dyes and the solvent or between the dyes and the paper. Okay, so first we can tell, the 3 dyes is shown here. So the running the least polar should run fattest. Okay, so die C is the least polar because you said because it moves the fattest. And you can say it, because it is moved the fattest, but it still can't tell the reason. So because you need to justify the answer. Justify is the intermolecular interactions, intermolecular forces. So then you can say nonpolar dyes are more strongly attracted to the nonpolar solvent. That's why they can move faster. Okay, or you can say nonpolar dyes are least strongly retained by the polar paper. But I think the last sentence probably is the best explanation. You just say nonpolar dyes, or you say these polar dyes are least strongly retained by the polar paper. Get it? So first you write this sentence. Dye C is the least polar because it moves the fastest, and then explain non-polar dyes are least strongly retained by the polar paper. I explained that, but you don't need to tell that details because you don't need to explain in such a detail because you don't know what kind of material they used on the chromatography. Okay. Second question, which dye is present in the unknown sample? Okay, here because this experiment is not done on the same paper chromatography, so we need to calculate their RF separately. So, and here is the unknown. So because the solvent front are different, so but we can see this unknown is approximately in the middle of the origin and the solvent front. And in the three dyes, the closest one is dye A, is also in the middle of origin and the solvent front. Okay? So then you can explain like that. Dye A is present in the unknown sample. Then you need to justify. The unknown sample moves to a position that is midway between the origin and the solvent, and so does dye A. Okay, so if more accurately or mathematically, because I told you a lot of times math is always the best way to explain. So dye A has a retention factor, RF, that is close to, you can just write 0.5, not 0.50, okay, just write 0.5 on the chromatogram and with the three dyes, and the unknown also has a RF close to 0.5. Okay, so I think the second explanation is more scientific and quantitatively. Okay, so first you need to identify what it is. It's a dye A, and it gives a reason. So just use RF. Okay. And yeah, there are also some written explanations shown here. You can read by yourself, but still, what I talked about is the best way, and of course, the most concise and a very simple explanation, but make sure it's correct. Okay. All right. So if you don't have any question about this one, then we move to next question. Okay. The question 5 is about, let's say, thermal chemistry. Okay. It's a burning of, so here's the reaction, the combustion of an alcohol like that. Yeah, it's OH here means hydroxyl is alcohol. So the question is here. So a student performs an experiment to determine the enthalpy of combustion of 2-propanol, which combusts in oxygen according to the equation above. The student heats a sample of water by burning some of the 2-propanol that is in an alcohol burner as present below. The alcohol burner uses a wick of draw liquid up into the flame. The mass of iso-2-propanol combusted is determined by the weighting of the alcohol burner before and after combustion. Okay, so 2-propanol is usually we call it isopropanol. Okay, you all know the rubbing alcohol, right? Rubbing alcohol is just this guy, 2-propanol. But usually we just use 40%. That means the 6% of rubbing alcohol is water. Okay, so the design of this experiment is there. So we burn isopropyl, and so the combustion of it to produce a lot of heat, the heat up water. And when the experiment is done, okay, so we just measure the burners, weigh the burner's mass, and get the difference. The difference is the isopropanol consumed for the combustion. Okay, we know its mass. Okay, and on the other side, so we can see the table shown here. Apparently, we need to measure the temperature of water, its initial temperature and the final temperature. And also the mass of water should be known. Okay, so after the experiment is done, the mass of isopropanol combusted is 0.55 gram, very little. Okay, mass of water heated, so you can measure its volume in the beginning or just weight it directly. Okay, and the initial temperature is 22 degrees Celsius, final temperature is 51.1 degrees Celsius, and the specific heat of water is 4.18 joule per gram per centigrade. Then we have all the information for calculations now. So question A is calculate the magnitude of heat energy in kilojoule absorbed by water. Okay, they assume the heat released from combustion completely transformed into water. So although we know it's not possible because some heat will release into the air around it. Okay, but the question gives you this assumption, so we just use it. So we know the equation Q equals mc delta T. Okay, M is a mass. Mass is water. Don't use the mass of the alcohol. Okay, so I don't think you will make such a mistake. Okay, use the mass of the water. Okay, the times C is a specific heat, 4.18. It's better for you to copy all the units in it. Okay, then the temperature is final minus initial. Okay, we can see then we have this value shown here, 15,200 joule, then converted to kilojoule, because in the question they ask in kilojoule, so don't forget that. And double check the significant figures. 5 for mass, 3 for specific heat, and also 3 after the subtraction. You double check. Okay, there are 3 significant figures. Then you can have 3 significant figures here. Okay, and this is the first step to calculate the total heat absorbed by water. That's also the heat released by the combustion of isopropyl alcohol. Okay. So next one, based on the experimental data, if 1 mole of isopropyl is combusted, how much heat in kilojoule is released? Report your answer with the correct number of significant figures. Okay, so we know the heat released in the first question, okay, by the combustion. And the mass of isopropyl is shown in the table here, is 0.55 gram, okay? So here the question is just about 1 mole of this one. So there are several ways to do that. So if we have 1 mole, okay, 1 mole, then we have that kind of mass. Okay, this is its molar mass. So molar mass divided by its mass, you got to actually you should do the mass divided by molar mass. You got the number of moles. Then the heat produced by the by the combustion divided by the number of moles of the isopropanol. Then you have the heat released by the combustion of 1 mole isopropyl. So here, this answer is just combine everything together. So it make it a little bit confusing, but it's a better one, I believe, is in shown here. So here you can calculate like this: 0.5 gram of this isopropyl alcohol divided by its molar mass. Okay, it's a molar mass. You got its number of moles. Remember, you have 2 significant figures, but you can keep more in the middle of calculation. Then delta H equals 15.2 kilojoule in the, from the first from question A, and divide by its number of moles you got here. So this is clearer. You can separate them into 2 steps. Get the number of moles of isopropyl first, then to the division. You got a 1700 kilojoule per mole. Okay. So I think in the written answer, it's better. This is also good, but you need to reverse something, rearrange something, then do the calculation. Okay, it's also good, but I prefer you to write the 2 steps. It's clearer. Okay. So the answer is to keep 2 significant figures. It's better to write in a significant in a scientific notation. Okay. Question C. A second student performs the experiment using the same mass of water at the same initial temperature. However, the student uses an alcohol burner containing still the same thing. That is contaminated with water. Okay, that means it's not pure, which is miscible with water is miscible with isopropanol. The difference in mass and alcohol burner before and after the combustion in the experiment is also 0.55 gram. Would the final temperature of the water in the beaker heated by the alcohol burner in the liquid be greater than, less than, or equal to the final temperature of the water in the beaker and the first student's experiment? Justify answer. First of all, okay, if it's mixed with water, so it still can burn with a little bit of water, okay, still can burn. But when it burns, water will not be burned away with it, right? Because water cannot burn. So the only isopropanol can be burned. So water will not affect the combustion, okay, because it will stay in the burner, okay. The water will stay in the burner. Basically, what we can tell is here. Basically, if we can, but here the answer here. So he said the final temperature measured by the second student would be less than measured by the first student because the actual mass of what combusted will be less than 0.55 gram. I think this answer is wrong. But if we think more deeply, so the second part will be better. So we still can say the final temperature consumed by the second student would be less than measured by the first. We can see that the second explanation is a good one. The combustion of a contaminated sample will also require vaporization of water in the sample. So that means when you burn isopropanol contaminated water with water, so water within the isopropanol will be vaporized. The vaporization itself needs some heat. Okay, needs some heat. So the heat is from the combustion of isopropanol. So some of the heat released by the combustion will be absorbed by the contaminated water. You get it? So the heat absorbed by the water sample, okay, in the beaker will be less than the actual, but slightly less, okay? But apparently is less, okay? So that's the explanation. So first, you need to answer the final temperature measured by the second student would be less than that measured by the first student, because don't use the first answer, okay? The second is a good one. Combustion of the contaminated sample will also require vaporization of the water in the alcohol sample, okay? Let's take a look at the written answer here. So it's written like that. The final temperature of the water would be less than that of the first student's speaker. This is because of 0.55 gram of water contaminated the alcohol contains less moles of. So again, this explanation is not good. So I explained that already. The better explanation is that some of the heat is consumed by the vaporization of the water in the alcohol. Okay, so you cannot. So the explanation here is also wrong. It is wrong. Okay, so be careful about that, because it's not less. You still need to burn that much. Even burn. At least need to burn similar one at the same time, okay, at the same time. But just some heat will be, okay. So yes, that's, sorry, I made a mistake. Let's explain one more time, okay? So here, I think the first explanation is also acceptable. Sorry, I made a mistake here. So the actual mass of the alcohol shown here composition will be less than 0.55 gram. This is correct. It's less. It's less because it's contaminated with water. So the first, the second explanation is the heat will released by the combustion. Part of it will be absorbed by the water to vaporize with it. Okay, so my bad. Okay, I apologize. So the answer is still good. You just need to, but here I think you choose the first one. I think that should be enough because it's not pure anymore. But the actual mass of the isopropanol is less than 0.55 gram. Okay, so I think that's a good explanation already. Okay. So I just thought a little bit too much about that. So now you get it? So because it's not a pure 0.55 gram, actually in this mass of the alcohol is actually less than 0.55 gram, okay? All right. Okay, let's move on to the last question. So like I was said, the thermal chemistry is quite important in this exam. So every year in the AP chemistry exam, there are something about thermal chemistry. So this is the very important point in the exam. Okay. So the last question we are going to talk about is about equilibrium. Okay. So the question is here. Answer the following questions about the magnesium hydroxide, which is insoluble if you check the solubility rule for hydroxide, except 1A groups and some 1,2 groups. So magnesium hydroxide is not soluble. Okay. At 25 degrees Celsius, the value of solubility product constant KSP is 1.8 times 10 to the minus 11, so quite a small number. So here's a question. Calculate the number of grams of magnesium hydroxide. It gives you the molar mass that is dissolved in 100 milliliter of a saturated solution of magnesium hydroxide at 25 degrees. Basically, just calculate you calculate solubility. So the standard definition of solubility is the mass of a substance dissolved in 100 milliliter or 100 gram water. They are the same for water because its density is 1. Okay. So here we are. So KSP value shown here equals magnesium concentration times hydroxide concentration times 2. Oh, sorry, squared. So we can define, if you write the ice table, you can have a magnesium set is 2x, set is x, hydroxide is 2x per square. So that's why we had write x times 2x squared, and we have 4x cubed. So then we can solve this equation. In the end, we have the concentration, x equals 1.65 times 10 to the minus 4 millimeter, which is a magnesium cation's concentration, which is equal to, this is a 1-to-1 ratio to magnesium hydroxide. So that's the concentration, saturated concentration for magnesium hydroxide. Then we need to convert it, the mass of it in 100 milliliter solution. So we know its concentration is shown here. The volume is 0.1, 100 milliliter equals to 0.1 liter. And we converted the number of moles to mass. So we have number of moles, then we times molar mass. Then we have the mass of magnesium hydroxide in 100 milliliter water. Okay. This is a very typical calculation for solubility, the intercurve ratio between solubility and the KSP. Okay, let's take a look at whether we can. So sometimes it's better for you to write this equilibrium shown in the answer here. So you can write the equilibrium arrow here. You can write x under magnesium and the 2x under hydroxide. Then put them together like that. Still, you can still get the same answer. You can read the answer by yourself. Okay. Be careful. Don't forget to do the conversion, because x here. Okay. Here's 2x squared. Okay. Make sure you have this equation set first. Then finish the calculation. You know, the 1-to-1 ratio between magnesium cation and magnesium hydroxide. That's why it's 1-to-1 ratio, because when it's dissolved, you only have 1 in solution. Then don't forget that's 100 milliliter. So don't forget to do the conversion. Okay, so easy to make a mistake to just calculate 1 liter. Okay, then you got a wrong answer. Okay. Okay. So this is not too difficult. Just be careful. I also suggest to you write the ice table. Okay, it won't spend too much time. Okay, so just write a table and put x there, 2x there. Okay, then do the calculation. Okay, it will make it more it's much more clear. Okay. Next question. The energy required to separate the ions in the magnesium hydroxide crystal letters into individual magnesium cation and the hydroxide, both of them in gas, okay, vaporized. Okay. As present in the table below is known as the lattice energy of magnesium hydroxide. As shown in the table, the lattice energy of strontium hydroxide is less than the lattice energy of magnesium hydroxide. Explain why in terms of periodic properties and Coulomb's law. Okay, so the lattice energy for magnesium is greater than strontium hydroxide. So the simple explanation is that the strontium is its radius is greater than magnesium's. Okay, so based on Coulomb laws, of course, the smaller cations can have stronger interactions. So if you write this way, it's okay. So the answer is shown here. The strontium 2 plus ion is larger than magnesium 2 plus. So you need to write this one. This is the trend for the atomic and ionic radius, okay? Because it has additional occupied energy levels, or just additional shells, okay? Two more shells, okay, strontium. Coulomb's law states that the force of attraction between cation and anions is inversely proportional to the square of the distance between them, since the distance between magnesium and hydroxide is shorter than the distance between strontium and the hydroxide. The attractive force in magnesium hydroxide are stronger, and therefore its lattice energy is greater. Okay. So you can write this way. It's a kind of wordy. Let me take a look whether, let's take a look whether we have, okay, I can use a whiteboard to show you some other ways. So, but you definitely can write this way, but if you write some math, it would be even better. So let me share whiteboard. So we know there's an equation, force based on Coulomb law, okay? It's a proportional, we can use a proportional to Q1 times Q2. Sometimes we use a little q, okay? Don't use capital, but it doesn't matter. So it's also, and the distance between them, okay? So you have two charges, Q1, Q2. Here is the distance between them. So you have for example, you have a magnesium 2 plus here, hydroxide, you have two particles. So the distance between them is equals R equals radius magnesium 2 plus the radius. Here are the distance between them, the radius of hydroxide. So in the second case, so you have a strontium and hydroxide. They are equal. They are equal, but for these two terms, it's greater. So we can write that this is 1, this is 2. So then we can have the result. R1 is less than R2. And we know in the two cases, Q1, Q2 are all the same because the hydroxides are the same. Magnesium and strontium, both of them have 2 positive charge. So we put here the top part are the same, but the bottom part in the fraction, so we also can have R1 square is less than R2 squared. Then we can get F1 is less than F2. So here is for magnesium hydroxide. Here is for strontium hydroxide. Then you can explain why the lattice energy for magnesium hydroxide is greater than strontium hydroxide. Okay? Let me share. Okay, so you can of course write a paragraph, short paragraph like the answer shown here. But like what I said, so if you can put the equations like what I wrote here already, so insert them here, you can make it a much more powerful to explain. Okay. All right. So you can also read through that one. I use a whiteboard to explain that, and I think now I can stop the video. So later on, if you want to review my explanations, watch the video. I will send you the link for the video. Okay, it's saved on the Zoom cloud. So later on, so I didn't record the previous lessons, but since now I will record all the lessons, so you can review when you want to go through the questions. Okay. All right. So that's what we do for today. And next time we are going to talk about the 3 long questions for 2016. Okay. You need to try first. Okay. Then here, basically, in the class here. Okay. I just want to explain in more detail and give you some principles, then you can understand better. Another thing is about the format, how to write the answer correctly. Okay?
Okay. Thank you.
All right. So, oh, you cannot see me. Oh, now you can see me. Okay. So, always accept the invitation. Put it in your calendar so it will remind you. And in the invitation, there also the link for the Zoom room. Okay, so it's easier when it pop out on your laptop. Okay, so you can just click there so you can enter. It's easier. But I will send you invitation if I cannot see you. Okay, don't forget. So next time it's Thursday. It's 3 o'clock. Basically, it's 3 o'clock. So, but just I will talk to the Spider Smart about time. I hope we can set it as 2 o'clock. But now, because there's some conflict with some other class, so let's say it's 3:10 now. Okay. Right.
Thank you.
Good. You can watch the video later, but let me set first, okay?
Okay.
All right, bye. Have a good
Thank you.
one.
Bye.
Stay safe.
Have a nice day.
Yeah, you too. Have a nice day.